Well, thank you. It's a pleasure to be here at Ithaca High School to talk about Euler. This talk should have in it three things I particularly like: a great mathematician, a long-standing problem, and a very clever solution. So we're going to see all of this. Now, the great mathematician is Euler. So this is he, Leonhard Euler. You see he lived squarely in the 18th century, one of the towering figures of the Enlightenment. The problem, it's a hard problem. Now, you think a hard problem took me a half an hour to solve last night. No, this took 2,000 years. This is a really hard problem. It's in the arena of number theory. And some of you may have seen this, but number theory is just about the whole numbers. You know, 1, 2, 3, 4, 5. You all know evens and odds, primes and composites. That's sort of an issue. That's the realm from which this problem comes. And then the solution is surprisingly intricate. It's going to take a long time to work through this solution to see how he addresses this. But the neat thing about it is it requires nothing more than high school algebra, you know, and a sort of a comfort level with symbols. But you don't have to know the law of cosines or integration by parts or anything like this. So you should be able to understand everything I show you. That's the hope. You know, it's not over your heads, but it's just incredibly ingenious. Wait till you see what this guy does. He does very much with very little, shall we say. Okay, so a few words about Euler first. This is Euler, and I always show this slide because these two people were almost exact contemporaries. Leonhard Euler, Swiss, European, mathematician, physicist, worked in Russia, in St. Petersburg, in Berlin, Germany. And Ben Franklin, on this side of the Atlantic, this sort of multi-talented guy, a diplomat, an inventor, a scientist. They were two of the great Enlightenment figures. They never met each other, unfortunately, but they would have known about each other. And they were both members of the American Academy of Arts and Sciences, interestingly. Franklin helped start that. And Euler, the year before he died, was made an international member and got a letter from the US saying, would you like to join? And he said, yes, thank you very much, but I can't attend meetings because I'm in Russia. So they're both, you know, kind of parallel figures with parallel dates, and they both have weird taste in clothing. I think you can look. I mean, if anybody knows what in the heck he's wearing on his head, you know, what is this? And then Franklin seems to be wearing a dead animal around his neck. I'm not sure what this is, but anyway. So these are the two great people. It's Euler we're going to talk about. Now, Euler's work is off the charts in both quality and quantity. And we'll see the quality when I show you him doing this great theorem I'm going to show you. But I wanted to mention a few things about the quantity of Euler's work, because no mathematician ever produced more mathematics than him. He's the record holder, the most prolific mathematician ever. And here's a way to see this. He died in 1783. He had, at that point, published hundreds of papers and books, but he wasn't done just because he was dead. Because in the next 47 years, he published 159 more papers while dead. These were things that were, you know, in his desk, things that were in press, things that, you know, he had given an address but not ever written it up. So they put this together. That's not bad. But wait a minute, 1844, a great year. 61, new papers, still dead. And a few years later, 8 more. So you add this all together, and he published 228 papers after he died. No other mathematician has ever done this, nor will they. 228 papers while alive is an amazing achievement. You know, 28 papers is an amazing achievement. This is just incredible. You know, how did he do this? And he did much of this while partially blind, and some of it while totally blind. Euler lost his vision at age 55 or something like that. It kept going, even though he couldn't see. He would just dictate his great mathematical results. Now, in 1910, someone named Gustav Ennerstrom decided to catalog all the things Euler had published, make a big, you know, list of these, and he counted 866 books and papers. And he wrote up a catalog where each of these had a little paragraph describing it. The catalog of Euler's work is 388 pages long. That's not the work. That's just the synopsis, the catalog. The next year, the Swiss Academy, because Euler was Swiss, decided they would publish his opera omnia, all of his works. They would take all these 866 things, reset the type, and put out the complete Euler opus. And in 1911, the first volume came out. And then in 1912, a volume came out. And the next year, a volume came out. And they're still coming. They're not done. And the volumes, here I brought one just to show you, these are not tiny things. This is a volume. At the moment, they're still working on this. There's 75 volumes, so this has 74 cousins. There are over 25,000 pages of Euler's work. I can't imagine reading 25,000 pages of this stuff, and he wrote it. So, you know, there is nobody in mathematics like this. So yes, the quantity of his work is off the charts. But the quality of his work is what we want to talk about. As I say, I'm going to be in the realm of number theory. So here's the key idea. This is an old definition that went back to the Greeks, BC. Two numbers, m and n, are amicable, which means friendly, if each is the sum of the proper divisors of the other. That's the definition. Now, before I proceed, how many have ever heard of this? Just curious. Is this anything anyone's ever seen? A couple, the senior types, yeah, and a few of the younger kids. Okay, so the first thing you got to do is give an example, because this is kind of hard to follow. Here's the example: 220 and 284. These are friendly numbers. These are amicable, and here's why. What you want to do is look at the proper divisors of 220. So that means you're looking at whole numbers that divide evenly into 220, but proper means they're not 220 itself. They're smaller. So there they are. All the divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Now, 220 is also a divisor, but it's not proper, so we don't count that. If you add these up, you get 284. You can check, trust me on that. You get 284. Now, you look at 284. What are its divisors? 1, 2, 4, 71, and 142, and 284, but that's not proper. If you add those up, you get 220. Each of these numbers is the sum of the proper divisors of the other. It's a weird reciprocity, and it's completely useless, right? I mean, this has no use at all, but it's cool. If you like number theory, you say, wow, that's neat. How strange is that? What a weird property. Can we find some more of these? Hey, I interrupt this lecture to bring a true story. I have a friend who, when he married the love of his life, he gave her a bracelet with the number 284 on it, and he has one he wears with the number 220. And this shows the friendship that they will always have. So I throw that out as an idea whenever you guys need this, I mean, it's very sweet and very nerdy, right? But, Okay, so there's amicable numbers. Now, here comes the brief history of amicable numbers. The Greeks knew that pair. Somehow they had stumbled upon 220 and 284, and they saw this reciprocity, and they sought others. Let's find some more. And they couldn't. These are not easy to find. So they found no others. And nobody does until the 9th century, when the Islamic mathematician Tabit ibn Qurra finds a rule that generates 2 more pairs. So this was in Baghdad, which in the 9th century was the center of mathematics on the earth. This was the great mathematical center. He now had 2 more, so there were 3 pairs altogether. But apparently, Tabit's rule did not make it back to Europe until just recently. So people in Europe didn't know of Tabit's 2 numbers. They thought there was just the 1 pair. So they're sort of attacking this problem after the Renaissance. And in the year 1636, the great French mathematician Pierre de Fermat finds another pair. And it's this: 17,296 and 18,416. So if you take all the proper divisors of 17,296, they add up to 18,416, and vice versa. Guess what? That's one of Tobit's numbers. What Fermat had done was just go down the same path that this Islamic mathematician had gone down centuries before. But Fermat didn't know that Tobit had done this. So he was very proud of this, even though it was a rediscovery. Okay, now in 17th century France, there was a great rivalry between Fermat and Descartes. They hated each other. And Fermat just found a pair. Now it's Descartes' job. If he's going to not be, completely humiliated, he's got to find a pair. So he goes to work trying to find his own amicable pair, and 2 years later, he does. And it's this pair. 9,363,584, 9,437,056. In your face, Fermat. That's what that is, sort of. If you really love your boyfriend or girlfriend, give them a bracelet with that number on it. Maybe it has to be a belt, I don't know. But guess what? That's the other of Tobit's numbers. These are the low-hanging fruit of amicable pairs. These are the easy ones. And what Fermat and Descartes had done was just go down the easy path that Tobit had done centuries before. Okay, so that's the three pairs. And now a century passes, and nobody can find even one more. These are hard. So nothing happens until Euler comes along in 1750. And he writes a paper, and this is it. And if you got the handout, you'll see that. It's called De Numeris Amicabilibus, on amicable numbers. Of course, it's in Latin. I put this up here because it lets me say amicabilibus, which is one of my favorite words. It just brings a smile to your face to say that. I share that with you. So, De Numeris Amicabilibus. If you look here in the second paragraph, you'll see as Euler starts his paper, 220 and 284. People always give that as an example. Okay, so we had the three pairs. Euler comes along in 1750, and in this paper, he finds 58 more pairs. So the world supply went from 3 to 61 in one paper. He saw something that no one else had seen and blew the problem out of the water. And, there's nothing you can say in response to this except amicabilibus, right? Yeah, all right, yeah, okay. All right, so I want to show you how he did it. Now the cartoon of how he did it is this. He had an idea, right? So this is, there it again, there we go. So he had an idea. So I'm going to show you what his idea was. And we're going to follow him until we find a new pair right here. New in the sense of 1750, it would have been new then, using his technique. And then I'm going to send you away with with a hint to find a few more on your own, which you'd be blazing new ground. Remember, this is cutting edge mathematics on Earth in 1750. Okay. It starts with this idea. And there's a whole bunch of great steps in this proof, but none is greater than the first one. Euler says, we're going to let sigma of n be the sum of all the divisors of n. All the whole number divisors. Now you would say, wait a minute, Euler, we want just the proper divisors for the amicable number stuff, which is true, but he realized this was the more fertile approach. So sigma of n is the sum of all the divisors of n, including n. So, example, how about 15? If I wanted sigma of 15, I just have to go find all the divisors of 15. 1, 3, 5, 15. Whole numbers that divide evenly into it. And add them up, and you get 24. Okay, so that's sigma of 15. This is called the Euler sigma function. Hey, what's sigma of 6? 12, right? 1 plus 2 plus 3 plus 6 is 12. Hey, what's sigma of 7? 8, because what are the divisors of 7? Just 1 and 7. What's sigma of 11? 12, 1 and 12. Yeah, can you see that there's a little theorem here? P is prime if and only if, what will sigma of P be? 1 plus P, or P plus 1, I wrote, yeah. Because a prime, every number is divisible by 1 in itself, and so the sigma is at least 1 plus the number, and if there's nothing else, that makes it prime, and conversely. So this is important. Sigma is a way of characterizing primes. Sigma of P is P plus 1, means it's a prime. Now Euler sees this theorem. This is an interesting theorem. If P and Q are different primes, like 3 and 5, for instance, then sigma of the product PQ is the product of the sigmas. It's almost like the sigma, distributes across there, and its sigma of PQ is sigma P, sigma Q. This is called the multiplicative property of the sigma. And I should show you a proof. Why is this? Because we're going to need this. But it's not hard because of the limited nature of the divisors of PQ. And if you think about it, if you have a number PQ and they're prime, what can divide into this product? 1 and PQ, but what else? P, Q, and nothing else because of the primality. So here's the proof. Sigma of PQ is 1 plus P plus Q plus PQ. Those are the divisors of PQ because P and Q are prime. And now here's what you do. You group the first two, 1 and P, and for the second two, Q plus PQ, factor the Q. Right? So now you have 1 plus P plus Q times 1 plus P. Now you factor the 1 plus P, and you'll get 1 plus P times 1 plus Q. But P is prime, so what is 1 plus P? Sigma P, and Q is prime, so what is 1 plus Q? Sigma of Q. And there's the proof. It's not very long because of the limited nature of what the divisors can be if P and Q are different primes. Okay? And so a little algebra, but there you go. So suppose I had known this rule, and I do this again. I want sigma of 15. Here's the easy way to do it. You say 15 is 3 times 5. Different primes. So sigma of 15, sigma of 3 times 5 is sigma 3 times sigma 5. But what's sigma of 3? 4. What's sigma of 5? 6. 4 times 6, 24, as we saw up above. But here I don't need to write them down. I don't need to write down all the divisors because I know what that sum has to be. So that's a key, it's a property of the sigma that makes it so important. But Euler recognized more than this. He knew that if two numbers have greatest common divisor 1, so A and B have GCD, I don't know if you know that, greatest common divisor. So like, I don't know, 9 and 25, right? Those numbers aren't prime. 9 and 25 aren't prime, but the greatest common divisor is just 1. They don't have any common factors. If this is the case, then this distributive property, if you will, this multiplicative property holds as well. So sigma of AB is sigma A, sigma B. Even if the numbers aren't prime, as long as they have no common factors. And this is a very useful tool in breaking down numbers to figure out what the sigma is going to be. So for instance, if I said, what's sigma of 585? Strange choice, but I'm going to write it right here. As if we might see this again, right? Sigma of 585. What you do is, you don't write down all the divisors of 585. I mean, you could, and then add them up. You could, but then you'll be done sometime tonight, with that problem. But instead, you break it into a product of relatively prime pieces, 5 times 9 times 13. And then you let the sigma go across, sigma of 5, sigma of 9, sigma of 13. What's sigma of 5? 6. What's sigma of 13? What's sigma of 9? 13, right? Because that's not a prime, but what divides into 9? 1 and 3 and 9, that's 13. So if I multiply the 6 times the 13 times the 14, I get 1092, which I have just written right here. Okay. So remember that. We'll be back to that. Okay. So the sigma can be used to, or this rule can be used to find the sum of the divisors of numbers. And if you did spend all night adding up all the divisors of 585, I promise you, you'll get 1092, but this is easier. Okay, so now, let me go back to the definition of amicable numbers and recast it in terms of the sigma. Remember, numbers are amicable if each is the sum of the proper divisors of the other. But Euler says, look, this is what that's going to amount to. M and N are amicable if sigma of M minus M is N, and sigma of N minus N is M. And can you see why? What's the sum of the proper divisors of M? Well, sigma of M is all the divisors, and then you've got to take the M away. So this is the proper divisors of M, and that would be N, and this is the proper divisors of N, so that would be M. So this is how sigma gets into this picture. And now he does something even better, because he fuses these two conditions here to this. He says, they're going to be amicable if and only if, you see from the left-hand equation, take the m over, and sigma of m is m plus n, and on the right-hand equation, take the n over, and sigma of n is also m plus n. So you get this one nice, efficient way of saying what amicable numbers mean. Sigma of m is m plus n is sigma of n, and if that condition holds, I got amicable numbers. That's what you're looking for. Okay, everybody with me so far in this? This is, again, nothing, just no trigonometry here, but okay. So now this is where we're going to attack this. And so what Euler says is, all right, I'm going to pose a structure for my amicable numbers. I don't really know any more amicable pairs, but let's suppose they have a certain structure and see if I can use that equation I just had up there, sigma of m equals m plus n equals sigma of n, to sort of show me where to look. I mean, there's infinitely many numbers. I need to kind of narrow the field. That's what he's up to. So here's what he says. Let's suppose m has the structure a times p times q. And let's suppose n has the structure a times r. And we're looking for, and suppose they're amicable. And let's specify what we got here. The p and the q and the r are primes. And they're different. And the a is going to be this common factor that is relatively prime to the p, q, and r. So it's like the GCD of the two. So p could be 3, q could be 5, r could be 7, and a could be 16 or something. So you got some primes and you got this other piece. Now, he's not saying that every amicable pair has to look like this, but if it looks like this, then what can we tell about the a and the p and the q and the r? Can we use this to help us find a new pair? Okay, so that's the structure. Now, remember the key equation we just had. Sigma of m equals m plus n equals sigma of n. He takes the two extremes and starts with that. Sigma of m would have to be sigma of n. So because of that, we fill in what m and n are. M is APQ, and n is AR. So sigma of APQ equals sigma of AR. Okay, now, I'm ready for my little rule. The sigma distributes as long as these guys are relatively prime, which they are. So on the left, instead of sigma of APQ, you're going to have sigma A, sigma P, sigma Q. And on the right, instead of sigma of AR, you'll have sigma A, sigma R, because of the relative primality here. Okay, now, if they throw this at you, you don't have to be Euler to know what to do next. What do you do with that? Cancel the sigma of A's, right? There's a sigma of A on both sides. So the magic of PowerPoint, there they go, gone. Okay. Hey, but wait a minute. P is prime. So what is sigma of P? P plus 1. What's sigma of Q? Q plus 1. What's sigma of R? R plus 1. Because he's saying P, Q, and R are primes. So now we're down to this fact, that if this is going to work, P plus 1 times Q plus 1 has to be R plus 1. So as you pick your primes, this has to be the way to pick them. Don't pick anything else because it's not going to work. This is necessary. Okay, so P plus 1 times Q plus 1 is R plus 1. That doesn't give me any amicable numbers yet. We're way far from getting the amicable numbers yet, but just keep, hang on. All right, so I'm going to do something now which he does. Euler always loved replacing letters by letters, doing substitutions. So he's going to let x be P plus 1 and y be Q plus 1. And let me just back up. So what he's going to do is let this be x, P plus 1, and that be y, Q plus 1. So you're allowed to do that. You can make a substitution. So x is P plus 1, y is Q plus 1. So what's P? Well, P will be x minus 1. Just solve the first one. And what's Q? That'll be y minus 1. But better yet, what's R? And you see, remember from this condition that I just had, P plus 1 times Q plus 1 is R plus 1. If the P plus 1 is x and the Q plus 1 is y, that's like saying xy is R plus 1. So what's R? Xy minus 1. So I'm going to call that condition star. Now, why did he do this? Well, to find his amicable numbers, he needs to know A, P, Q, and R. Now he doesn't need all those. Now he just needs to know A and X and Y. Because if you knew x and y, you would calculate p, q, and r from these equations. So he's just limited the number of variables. He's got one less thing to find. But we still haven't found anything yet, but okay. Okay, everybody with me on that? All right, now what? Well, there was another condition. Remember, to be amicable, sigma of m equals m plus n equals sigma of n. And here we were using the extremes, sigma of m equals sigma of n. But we've got to use that intermediate piece too. So we also know that sigma of m is m plus n. So now he's going to fill in m is APQ and n is AR into this one and see where that carries him. All right, so sigma of m is going to be sigma of APQ. M is APQ and n is AR. Okay. What am I going to do with sigma APQ? Same thing, sigma A, sigma P, sigma Q. But on the right side here, there's not much I can do with this, except I guess I'll factor an A out. So I'm going to get sigma A, sigma P, sigma Q. On the right side is A times PQ plus R. Okay. Now, I can't do anything with the sigma A. Remember the last time we canceled the sigma A's. Can't do that. Hey, but I can do something with sigma P. P is prime, sigma P, P plus 1. Sigma Q, Q plus 1. So I fill those in. So now I know that sigma of A times P plus 1 times Q plus 1 is A times the quantity PQ plus R. And now, if you think Euler's lost here, he's adrift, you know, what's he doing? You know, so did I when I read this. But he's not lost, believe me. He's just not there yet. He's working. Hey, here's what I'm going to do next. This has P's, Q's, and R's. I don't want that. I want X's and Y's. But up here, I have ways to change them. Like where this P plus 1 is, I'm going to put an X. Where this Q plus 1 is, I'm going to put a Y. And I can, on the right side, where the P, the Q, and the R are, I'm going to fill in those equations. So let's see what happens now. There's where we were, right? So that's the one we had. P plus 1 is X. Q plus 1 is Y. Whoops, I just went backwards, didn't I? There we go. And on the right side, the P is X minus 1. The Q is Y minus 1. And remember, the thing with the star on it told me that the R is XY minus 1. So now the P's, Q's, and R's are gone. X's and Y's are in. All righty. Yeah. What do we do with this? Well, I'll leave the left side alone. But in the right side, in those brackets, I can, multiply out. So can you see what's going to happen in the brackets? You're going to get two xy's. Can you see it? An xy here, when these multiply, and then there's one. You're going to get minus an x, when I use the FOIL method, if you want. You're going to get a minus a y, and the ones are going to cancel. You see that? Minus 1 plus 1. So it's going to come down to this. Sigma of A times xy on the left is A times the quantity, 2xy minus x minus y. And again, nothing but high school algebra. Algebra 1, elementary algebra. Okay. Now, what's he want to do with this? He wants to solve this for y. Okay. If you're going to solve this for y, that means anything that doesn't have a y in it goes to one side, and everything that does have the y in it goes to the other, and then you factor. And the only thing that doesn't have a y in it is this minus ax. So that's going rightward. It becomes plus ax. And then everything else has a y in it, and I'm going to factor the y out. So you see this piece is 2axy. So there's the 2ax. I factored the y. Here's the sigma a times xy. When this comes over, it becomes minus sigma ax, and I factor out the y. And finally, here's a minus ay, and so I factor out the y. And now if you divide by that coefficient, you'll get what y is. Y is ax over this thing in the square brackets. But wait a minute, he's going to do something here too. These first two terms have an x in them, 2ax minus sigma ax. So how about we write that as 2a minus sigma of a times x, and then that minus a tacked on the end. So that's what y is. Ax over 2a minus sigma of a times x minus y. And I still don't see any amicable numbers here, but okay, keep going. We're getting there. Everybody okay? Nobody's passing out or, okay. All right, let me put that up here. Now, guess what he does? he says it's time for a new substitution. We need some more letters. And we say, Euler, wait a minute, you've already used M, N, P, Q, R, X, and Y. And he says, yes, but there's 26 letters in the alphabet. I still have room. So he's now going to say, let A over 2A minus sigma of A equal B over C in lowest terms. So now if you think about it, A is going to be a whole number, 2A is going to be a whole number, and sigma of A is going to be a whole number. It's the sum of all the divisors of A. So this is just going to be a fraction here, A over 2A minus sigma of A. If it's already in lowest terms, then the B is the numerator and the C is the denominator. If it isn't, if it was like 16/14, then you'd reduce it to 8/7, and the B would be the 8 and the C would be the 7. So you want to reduce this. What's neat about this, however, is if you look at the Y up there, it has that square bracket 2A minus sigma of A. But I can solve this lower equation for 2A minus sigma of A, which will be AC over B. Can you see it? If I solve for that denominator, it'll be AC over B. I'm going to replace 2A minus sigma of A by AC over B. And now something cool happens. The A's cancel. The A, he doesn't need. He's found a way around it. So all those A's are going to wipe out. Now, it's going to leave me with an X on top and a BC over X minus 1 on the bottom. And while we're at it, let's clear fractions by multiplying through by B so we don't have a fraction within a fraction. And if you do the algebra on this, the A's are gone. You hit the top with a B, you get BX. Hit the bottom with a B, you get CX minus B. I'm sorry?
How can you get y equals ax over something? Can you show the calculation?
Just do it that y equals ax over step on the bottom of that.
Okay, so everybody's okay.
Except for that last little bit. We got lost.
You got lost? All right, so are you okay to here? No. Okay, so I solved for this denominator. So what is 2A minus sigma of A? It'll be AC over B. In other words, move this to there, put the B down, put the C over. So this is this. 2A minus sigma of A is AC over B. If you solve this for 2A minus sigma of A. Yeah, got it? And then I canceled and cleared fractions. Okay, raise your hand. We're good? Okay. Now, that's why. We're almost ready to start looking for our amicable numbers. But now what he says is look for CY minus B. That's what he wants to really look at. CY minus B. Now, there's the C. The Y we just did. This goes in here for the Y. So CY is C times BX minus, BX over CX minus B. Minus B. And if you get a common denominator here in this thing, it's going to be CX minus B. Notice what happens when you put, in other words, I'm going to smush these two terms together over CX minus B. Here you'll get BCX on the top. Here if I put CX minus B, I'll get minus BCX, and then plus B squared. And the BCX's will cancel, and it's just that. So CY minus B is B squared over CX minus B. And then, I promise you, this is the last critical equation. Cross-multiply this. Take this denominator times that, and you get the critical equation Euler's after. That Cx minus b times Cy minus b is b squared. And with this information, he's going to find 58 new amicable pairs. Or we'll find one in here at least. Okay. Now, let me see. Here comes the strategy now. Before we start hunting, let me just summarize all this. And this is what's on the back of your sheet if you want to follow the steps. What he's going to do is start with A. You can pick anything you want. He's going to then look at A over 2A minus sigma of A, reduce it to lowest terms, and that'll give him B over C. So now he knows what the B and the C are. He then goes to this critical equation, Cx minus b times Cy minus b is b squared. Since he knows B, there'll be numbers up here. And there's not many ways you can multiply the two numbers to give you b squared, so he can actually list the candidates. So he'll know what cx minus, or cx minus b could be, what cy minus b could be. From this he can find x and y. From this he can find p, q, and r. From this he can find m and n, and there's his amicable numbers. That's all there is to it, right? So this is how he's going to proceed. So let's start with a equals 4. So this is like the seed. The a is like the seed you plant from which these numbers will follow. So I'm going to pick 4. Why 4? You'll see. There's a reason I'm picking 4. Right? I'm not telling you just yet. Okay. Now, the first thing you got to do is a over 2a minus sigma of a. So a is 4. 2a is 8. What's sigma of 4? 7. Can you see it? What's the divisors of 4? 1, 2, and 4. Add them up, you get 7. So you get 4 over 8 minus 7, which is 4 over 1, which is already in lowest terms. So the b is the 4, and the c is the 1 for this example. Now you look at this. Cx minus b times cy minus b is b squared. B is 4, c is 1. So this becomes 1x minus 4 times 1y minus 4 is 4 squared. In other words, x minus 4 times y minus 4 is 16. Okay? So now we're to that step. Now, what I have to do then is find two numbers that multiply to be 16. There's not many places to look. These have to be whole numbers. And I can just run through the options and maybe find an amicable number. And he does it by actually writing down the key equation, x minus 4 times y minus 4 is 16, and making a list. So I'm going to do this on a chart, which is what he does. OK, so first issue, x minus 4 times y minus 4 is 16. So here I got to put down two numbers whose product is 16. Well, how about 16 times 1 as a start? OK, so I don't know. We'll try it. All right. So x minus 4 is 16, y minus 4 is 1. OK, now help me fill in the chart. If x minus 4 is 16, what's x? 20. Right? If y minus 4 is 1, what's y? 5. Remember, p was x minus 1, a prime. So if x is 20, what's p? 19. Prime? Prime, right. Y, a q is y minus 1. If y is 5, what's q? 4. Prime? No. Ah. All right. A dry hole. This is a dry hole. Most of the things he tries are dry holes. These aren't easy to find. So usually you run into a dead end, because remember, these have to be primes, and 4 isn't a prime. But there's other ways to multiply two numbers and get 16. So 16 times 1, how about 8 times 2? All right. If x minus 4 is 8, what's x? 12. If y minus 4 is 2, what's y? 6. Back up 1. What's p? 11. What's q? 5. Hey, so far, primes? Yeah. All right. One more. R, xy minus 1. 72 minus 1 is 71. Prime? Yeah. So now he's hit pay dirt. And now that he knows A, which was the seed, 4, he knows PQR, he builds his numbers. Remember, M was APQ and N was AR. So M is APQ, which is A, 4, times 11 times 5. And N is 4 times 71. And 4 times 11 times 5 is 220. And 4 times 71 is 284. Good news, bad news. Wait. No. Premature clapping. That's good news, bad news. Good news, they're amicable. Bad news is they already knew that. So that wasn't good. In fact, if that was what happens with the seed of 4, you get the Greek pair. If you use 16, you get Fermat's pair, 2 to the 4th. If you use 2 to the 7th, 128, you get Descartes' pair. So what Tobit had discovered and what Fermat and Descartes rediscovered was how to do this game with A equal a power of 2. But no other power of 2 yields a pair that isn't a number that's got 100,000 digits or something. So this is where that ends. But Euler didn't require that A be a power of 2. That was the advantage. It could be anything, unlike these limited kinds. So that's why he got more choices. So here, for my last example then, I'm going to pick A equals 585, which is one of the ones Euler picked. So play the game again. A over 2A minus sigma of A is 585. You double 585 and you get 1170 minus sigma of 585. What in the heck is sigma of 585? Ah, there we go. It's 1092, as we saw by using the rule. So this comes out to be 585 over 78. And believe it or not, that's not in lowest terms. You can divide top and bottom by 39, and you get 15 halves. So now what's B? 15. What's C? 2. There's your equation. Cx minus b, cy minus b is b squared. You put in 2 for C, 15, 2 for C, 15 for b, and you get 2x minus 15 times 2y minus 15 is 225. And now we go to the chart and try to find something. All right, so I need 2 numbers that multiply to be 225. How about 225 and 1? I'm going to start there. 225 and 1. If 2x minus 15 is 225, 2x is 240, x is 120. If 2y minus 15 is 1, 2y is 16, y is 8. Back up 1. P will be 119. Prime? Prime? What? Divisible by 7. Yeah, that's not a prime. It looks like a prime, right? It's got a 9 on the end, but okay, so that's dry hole. Remember, these have to be primes. 119 is divisible by 7. Okay, here now let's try 75 times 3. That also is 225. If 2x minus 15 is 75, 2x is 90, x is 45. This isn't looking good, right? But 2y minus 15 is 3, 2y is 18, y is 9. But as soon as I back up from 45, no, not prime. All right, how else can we get 225? How about 45 times 5? If 2x minus 15 is 45, 2x is 60, x is 30. That's promising. 2y minus 15 is 5, 2y is 20, y is 10. Back up 1, 30 goes down to 29, prime. 10 goes down to 9, not prime. All right. Most of these are dry holes. Right? Now, there must be a solution coming, or I wouldn't be showing you this, right? The next one is 25 times 9. Now, same game. 2x minus 15 is 25, 2x is 40, x is 20. 2y minus 15 is 9, 2y is 24, y is 12. Back up from the 20, you get 19, prime. Back up from the 12, you get 11, prime. Drum roll, important moment here. What about R? R is this product. 240 minus 1 is 239, prime. And so he hits 1. And now you build your number. M is APQ, N is AR. A was the seed, 585. So M is 585 times 19 times 11, 122,265. N is 585 times the R, 139,815. And when Euler wrote that down in 1750, no one had ever known that was an amicable pair. That was a new pair. And yet, I hope you could follow this and see that, you know, as long as you have an IQ of 4 digits like Euler, this wasn't so hard. You just follow along, and there it comes. So if you want to try this at home, let me give you some other seeds, and you can get your own new amicable pairs, 92, 819, and 5733. And the hard part of these is this step, is figuring out the sigma of these. You have to factor these down and break them apart. And then you just follow the game, and you'll get some new pairs. So, you know, and then I should say that Euler didn't just limit himself to AP, Q, and AR. He also then went back and did this all over again if M was APQ and N was ARS, and got some new equations and got some more pairs. And maybe M was APQR and N was AST, and he got some more that way. And that's how he built up his collection to 58. So, you know, what can we say? Amicabilibus, right? Yes, way to go. And way to go, Uncle Leonhard. So there you go. It's a little icing on the cake. I'll show you another Eulerian result. This one, more famous. You might have even run into this. This is called the Basel problem. And this was the first big splash he made. He was 27 when he solved this. It had been a problem that was around for a generation, and no one could do it. And you know, I guarantee you, lots of people were trying. And so whoever does it is going to be famous. And this made Euler famous, the Basel problem. So let me begin where it began, with a challenge from Jakob Bernoulli. And that's a name you might have run into in one of your courses here. Bernoulli was a great mathematician. And the challenge was this, to find the exact value of this infinite series. And so you see, this is like Calc 2 or Calc 3 stuff with infinite series, but it's that series. 1 plus a fourth plus a ninth plus a 16th. And can you see what these are? These are the squares, the reciprocals of the squares. The next one is 149, right? So what does this add up to? Exactly. This is what Jakob tried to get. And he was unable to answer it. He was very, very smart, but he couldn't figure this out. This is what we would write it the sum 1 over k squared. Would call it a p series if you've had calculus, and p is 2. But they didn't have all that terminology or notation back then. Now, Jakob couldn't do it. Jakob Bernoulli couldn't do it, but he made a nice start. Let me show you how he got at least some information. There's the series. 1 plus a fourth plus a ninth. So Jakob says, let's write it this way. Instead of 1 plus a fourth, 1 over 2 times 2. Instead of a ninth, 3 times 3, 4 times 4. And now, I'm going to change these denominators in this fashion. I'm going to put the comparison series up here. So instead of 1 over 2 times 2, I'm going to put 1 over 1 times 2. Instead of 3 times 3, I'm going to put 2 times 3. You see, I'm reducing the left-hand number by 1. And I need to put an inequality sign here. These aren't the same. Is the top bigger than the bottom or smaller than the bottom? Which way? In other words, which is the smaller series, the one up top or the one down below? Top is smaller, right. Because this is a fourth, and this is a half, which is bigger. This is a ninth, this is a sixth, which is bigger. So I made it bigger, so my inequality is less than. So I don't know, this isn't going to tell me the value of that series, but I'm comparing it to this series, which is 1 plus a half plus a sixth plus a 12 plus a 20th if you multiply out. So the series in question, Bernoulli's series that he can't figure out, is less than that series, 1 plus a half plus a 6 plus a 12. And so we're doing a comparison test. And if you've had calculus, you might have heard about this for series convergence. You do a comparison test. This is the earliest example I know of anybody doing a comparison test. So this was like where that started. But now that just sort of pushes the goalpost down the field. All right. If I want to do that, I got to know this one. So what's this series? Well, they could do that one. And here's how. You see this 1/2 here? Nah. Write that as 1 minus a half. You see the 1/6? Nah. A sixth is a half minus a third. A 12th is a third minus a fourth. A 20th is a fourth minus a fifth. So I replace all those fractions by differences, and now what happens? They cancel like crazy, right? The minus 1/2 and the plus 1/2 go, the minus a third and the plus a third, the minus a fourth and the plus. Everything cancels, and what's left here? 2, yeah, this one and that one. So the series that we want is less than 2, which is what that series is. So Bernoulli knew that. So, you know, that's something. It converged, we would say, to something less than 2, but he wanted to know what exactly. And he couldn't do it, and so he writes this, and he publishes this plea. If anyone finds and communicates to us That which has thus far eluded our efforts, great will be our gratitude. Please, can somebody do this? I need to know before I die. But he didn't. He died. He never knew what the answer was. Lots of people worked on this. His brother, Johann Bernoulli, worked on it, couldn't do it. His nephew, Daniel Bernoulli, couldn't do it. Leibniz couldn't do it. Nobody could do it until Euler comes along. Now, Euler tries this and very cleverly gets a numerical approximation. You can't, it's not the exact value, but you go out far enough and do some tricks and you can get a number. And what he decided was it's somewhere around that, 1.644934, which doesn't look like anything to me, it's just a decimal. And Euler was getting kind of discouraged too, and he said, it seemed most unlikely to be able to find anything new about this. But in 1734, he returned to the problem and said, against all expectations, I have found an elegant expression for the sum of this series. And he did it. He found the answer. Now, I'm not going to tell you the answer yet, I don't think. But have you seen this? Do you know the answer? What is 1 plus a fourth? OK, so it's an elegant expression. It's unbelievable. It's one of the great formulas in all of mathematics, because you'd never guess what the answer is. OK, so let me show you how he does this. There's 3 pieces you need to know. You just assemble 3 things. The first one, when is the sign 0? The sign? What's that have to do with anything? But that's how he's going to do this. So there's the graph of the sign, and its zeros are at 0, pi, 2 pi, 3 pi, 4, and minus pi minus. So you can see them there where it's crossing the x-axis. So you all know that, the zeros of the sine function. OK, so put that on the shelf. We're going to need that. The second thing you're going to need, you might not have seen, depending on whether you've had calculus, but it's the series expansion for the sine x, the so-called Taylor series for sine x. So if you've seen this, raise your hand. Just, how many have seen? OK. If you haven't, just trust me on this. But this is what the sine is. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. It's called the Taylor series. And Euler knew this. This has actually been around before him, so people knew this. So that's the second piece. And then the third piece you need is kind of specialized. And let me build to it. So let me just start with this sort of prelim. Suppose p of x is a quadratic second-degree polynomial, and you know that p of 0 is 1, which means its y-intercept is at 1. And you know that it has solutions a and b. X equals a, x equals b. Solve p of x equals 0. So suppose you have such a thing. Then here's how you can factor that. You can factor it as p of x equals 1 minus x over a times 1 minus x over b. Now, this isn't hard to see. Let's just check things here. What degree polynomial is this going to be if you multiply these? Quadratic, the 2 terms. That's good. What if you put 0 in for x? If you put in 0, you get 1 minus 0 over a times 1 minus 0 over b, which is just 1, as it has to be. Suppose you put a in for x. P of a will be 1 minus a over a times 1 minus a over b, but a over a is 1, so that just becomes 0. And if you put b in, you get 0 as well. So this is the right factorization. It's quadratic, it has the right intercept, it has the right roots. OK. Everybody all right in that? Just kind of an odd way to write it, but OK. Let's jump up to a third-degree polynomial. Suppose p of 0 is still 1, but now you have 3 roots, a, b, c. How do you factor? Now it's going to come out looking like 1 minus x over a times 1 minus x over b, and you get a new term, 1 minus x over c. It's cubic. You put in 0, you get 1. You put in a, b, or c, you get 0. Sure. And now Euler, being very bold, says, let's suppose you have an infinite degree polynomial. It just keeps going. But suppose that p of 0 is 1, and now your solutions are infinitely many, x equals a, b, c. Then he's perfectly happy to just extend the rule and factor p of x as 1 minus x over a times 1 minus x over b times 1 minus x over c forever. And this is dangerous. Things that work for finite things don't always extend to the infinite case, but he was bold, so he does this. So that's the third piece of the puzzle. OK. So now with that, we're going to solve the Basel problem somehow, right? So here's what he says. Everybody okay with the pieces? All right. He says to evaluate that, he's going to introduce an infinite degree polynomial, and this is the one he wants. 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, and so on. Infinite degree, goes on forever. All right, I want to factor this by that third result. So what's p of 0? What do you get if you put in 0 here for x? 1, right? Everything wipes out except that 1. So that's good. So that's 1. Now I need to know, to factor it, I need to know that p of 0 is 1, and I need to know all the roots. So I got to solve p of x equals 0. That looks terrible, right? How in the world are you going to do that? 0 equals p of x. 0 equals 1 minus x squared over 3 factorial plus x4 over 5. How in the world are you going to solve this for x? He knows. Here's what you do. There's the 0, and there's the right side. 1 minus x squared over 3 factorial plus x. And you make a fraction out of the right side. Put a line there, and multiply on the top by x and on the bottom by x. Which doesn't change things. Except, what x am I not allowing here when I do this? Yeah, x can't be 0, or else you have a 0 on the bottom. But otherwise, this is legit. If I distribute the x across the top, the x on the bottom stays there. Across the top, I get x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7. Every exponent goes up by 1. And what is that numerator? Sine of x. That's the Taylor series for sine of x. X minus x cubed over 3 factorial, and so on. So when I'm trying to solve p of x equals 0, I'm really trying to solve sine x over x equals 0. It becomes that. And so that, if you cross multiply, you need sine of x equals 0. And we saw where the zeros are for the sine. There they go. 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. And so those are like the a, b, and c. When I'm going to factor this, those are the roots. They're going to show up in the denominators. Except, wait a minute, one of these numbers we've got to throw out. 0 is not a solution to p of x equals 0 because we know p of 0 is 1. It's a false root. It is shown up here. But remember, we didn't even allow x to be 0 at all when we put it in the denominator. So we weren't considering 0, so we can't count it here. So 0 is out. So that's gone. So we have pi minus pi, 2 pi minus 2 pi. And now p of 0 is 1. We know the solutions, so now we factor. So here comes the exciting conclusion, comes from this factorization. So there's the p of x that we started with. 1 minus x squared over 3 factorial. And now on the other side, I'm going to factor it 1 minus x over a, 1 minus x over b, 1 minus x over c, where the a, b, c's are the pi, the minus pi, the 2 pi, the minus 2 pi. So you get 1 minus x over pi. You get 1 minus x over minus pi. You get 1 minus x over 2 pi. You get 1 minus x over minus 2 pi. 1 minus x over 3 pi. 1 minus x over minus 3 pi. Forever. It's an infinite product. Okay? Hey, this second term, let's write, instead of 1 minus x over pi times 1 minus x over minus pi, let's just turn it into 1 plus x over pi. The next guy's okay, 1 minus x over 2 pi, but the next one will turn into 1 plus x over 2 pi. 1 minus x over 3 pi, 1 plus x over 3 pi. And now, Euler says multiply the first two together. It's like a difference of squares, a minus b, a plus b. So when those multiply, you get 1 minus x squared over pi squared. The next two, what's that going to be? 1 minus x squared over 4 pi squared. The next one, 1 minus x squared over 9 pi squared. And you begin to see the 4, the 9, the 16 in the denominators. That's what we're trying to figure out, although we're not there yet, but it's looking hopeful, right? So this p of x, which was given up here by an infinite sum, is given down here by an infinite product. Same p of x, written in two completely different fashions. So there it is. And now for the end, he says multiply out the product. It's an infinite product. How am I going to do this? We don't have to go very far. So tell me this. If I were to multiply this out, what's the constant term? that's going to emerge? 1, right? Because this one would hit this one, would hit this one. So you're going to start with a 1. How many x to the firsts am I going to get if I multiply this out? X to the first power. Can't, right? Impossible. There's no way an x can show up here. The next candidate is x squared. So if I multiply this out, how many x squared you're going to get? Well, look, you'll see this term could hit all the other ones, and I'll get a minus 1 over pi squared x squared. This term could hit all the other ones, and I'll get a minus 1 over 4 pi squared x squared. This guy could hit all the other ones, and I'll get a minus 1 over 9 pi squared x squared. So there, if I factored out the x squared, that's the coefficient of x squared. How many x cubes are you going to get? Can't get an x cubed. How many x fourths you're going to get? I don't care. So I'm just going to call the rest of this stuff, right? There's whatever else is coming, I don't care about. Okay, so now what you do is look at where we are. The p of x, written that way, multiply it out with the stuff, and now these match, right? This starts with a 1, that starts with a 1. There's no x's up there, there's no x's down here. So the coefficients of the x squareds must be the same. What's the coefficient of the x squared up here? Minus 1 over 3 factorial. What's the coefficient of the x squared in the second line? It's that guy in the square brackets. Minus 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared. What's 3 factorial? 3 times 2 is 6. Let's change all the minuses to pluses. There's a 6. Factor out the pi squared, and you get 1 over pi squared times 1 plus a 4th plus a 9th. There it is. There's the series. Cross multiply, and the sum of the series of reciprocals of squares from the Basel problem is pi squared over 6. Absolutely unbelievable, right? Why in the world should it be that? I mean, where's the pi come from, you know? But here it is. Euler has done it. And when he published this, he became Euler with a capital E. He became famous throughout Europe because nobody else could do this. He solved the Basel problem. A couple of things before we leave. If you calculate pi squared over 6, it's less than 2, as Bernoulli had said. If you approximate it, it's about 1.644934, as Euler had said. So they'd been on the right track, but neither of those was the exact answer. And the exact answer is pi squared over 6. Let me just finish it up with two last slides. Here's what Euler wrote. Against all expectation, I have found an elegant expression for the sum of the series that, he says, I have found that 6 times the sum of this series is equal to the square of the circumference of a circle whose diameter is 1. You know, what? Why did he say it like this? But if you look at what he's saying here, if you take 6 times the series, that's the square of the circumference of a circle whose diameter is 1, but circumference is pi d, so that's pi d squared. But if d is 1, that's pi squared, and if you solve it, you get pi squared over 6. So he had a very funny way of telling the world about this, but we would write pi squared over 6. And you know, I'm almost ready to say amicabilibus again, because that's so cool, but we'll just say, way to go, one more time, Uncle Leonhard.